Now let's look at concurrency and parallelism. But before we go into the code, let's learn some basic terms. So what is parallelism? A condition that arises when at least two threads are executing simultaneously. Concurrency, a condition that exists when at least two threads are making progress. A more generalized form of parallelism that can include time slicing as a form of virtual parallelism, which means that kind of two threads are running. In reality, they might not be running simultaneously, but it feels to the user they are. But for example, one thread might get some time on the processor, then second thread might get some time on the processor, and they keep on switching. That's one example of concurrency. So concurrency is kind of more general than parallelism, because in parallelism it just executes simultaneously. Couple of few more things to learn. Program. A program is an executable file which consists of a set of instructions to perform some task and is usually stored on the disk of your computer. Basically, a program is just an executable file, right? For example, a Python program, a Java program, but Java is then compiled to machine readable code, right? But yeah, basically a program is an executable file which consists of set of instructions to perform some task and is stored on disk. What is a process? A process is what we call a program that has been loaded into the memory along with all the resources it needs to operate. It has its own memory space. What is a thread? A thread is the unit of execution within a process. A process can have multiple threads running as a part of it, where each thread uses the process's memory space and shares it with other threads. Now finally, two main concepts, multithreading and multiprocessing. Multithreading is a technique where multiple threads are spawned by a process to do different tasks at about the same time, just one after the other. This gives you the illusion that the threads are running in parallel, but they are actually run in a concurrent manner. In Python, global interpreter lock (GIL) prevents the thread from running simultaneously. And this is one of the limitations of Python, global interpreter lock, which kind of limits the multi-threading capability of Python. What is a multiprocessing? Multiprocessing is a technique where parallelism in its truest form is achieved. Multiple processes are run along multiple CPU cores which do not share the resources among them. Each process can have many threads running in its own memory space. In Python, each process has its own instance of Python interpreter doing the job of executing the instructions. So these are the basic things. What is a program? What is a process? What is a thread? Then multi-threading and multiprocessing. So let's first look at a very simple program. So for using threading, we will import a module called threading, and just to measure the time, like how much time it takes to execute something, we import time. So let's first define a worker function. Basically, it is just a simulation of some work. So basically it prints the starting worker thread, then it sleeps for 2 seconds, then it prints exiting worker thread. So how do we create a thread? Threading.thread target is equals to worker. So whatever you want to run, that is the target. And this just creates a variable which is a thread, but it has not started yet. So to start the thread, we use t.start. Then we print main thread is waiting for worker threads to finish. T.join is something where the program waits for all the worker threads to complete. Then we print main thread is exiting. You run it using shift enter as it is a notebook. See, it's running. It took 2 seconds or something and then finished. Now we are importing a couple of things. We import time, and from threading module we import thread and current thread. From multiprocess module we import process and current process. Now what we are doing here is that we are just defining two worker functions. One will simulate the IO bound worker and another one will be CPU bound worker. So this has nothing to do with really understanding the behavior of each. Let's look at each one of it. The first one is IO bound worker. Basically, it takes number of seconds and we just get PID, which is just a process identifier. We kind of get a thread name and process name, basic stuff, and then we print it, PID, process name and thread name. It is starting to sleep, and we sleep for some seconds, which is the input. For example, in this program, we have set it to 10 seconds, and then it prints the process finished, sleeping. So the goal is that this IO bound function is where we are using sleep function. So CPUs are really sitting idle and passing time. In CPU bound task, again, we just get process ID, thread name, process name. We start counting. And here we are trying to keep the CPU busy by counting. So it starts from count, which is a large number. I think it's 6 billion or something, 0.6 billion. So it's counting and then it finishes counting. So we have defined two workers, IO bound and CPU bound. One kind of does a simulation of IO bound task, another one does the simulation of CPU bound task. And we'll use it in 6 scenarios. So let's look at them one by one. So what is the first scenario? We perform the IO bound task twice, just one after the other in sequence, and we calculate the time. Let's run it. And yeah, these will take time because I have chosen a slightly larger input size. So it makes sense, right? Because we had set sleep to 10 seconds, and when we run it twice, it roughly takes 10 seconds each, so it's 20 seconds approx. And the second one we will do is we will run the IO bound task. We'll measure the time. So how measuring time works is that in the time module, there's a time function. So time.time gives us a start time. And then we again measure time.time, it gives us an end time. And end time minus start time is basically the number of seconds it took. So what we are doing here is that we are doing the same task with threading. So we create two threads for IO bound task, and whatever input it needs, this will be in the args. Then we start both the threads, we wait for them to finish, and then we print the time it took. The first one took 20 seconds for IO bound task. Let's see if threading helps. So threading takes 10 seconds, right? So for IO bound task, it is helping. Let's make a note of it. Approx 20 seconds, approx 10 seconds. So this one took approx 20 seconds. This one took approx 10 seconds. Let's go on. So at least multi-threading is helping us in IO bound tasks. That's one thing which we learn from here. Third one, we will run the CPU bound in sequence, no parallelism, nothing. Let's see how much time it takes. And the CPU bound task does a lot of counting. So basically the CPU is busy in some way. Let's run it. And it takes like a minute or something. So yeah. So we are doing nothing, just calling the CPU bound function twice in sequence and just measuring if we run it naively how much time it takes. And while this is running, let's run this also. What we are doing here is that we are just checking whether threading, multi-threading will help us in CPU bound task or not. So similarly for CPU bound task, we create two threads with the right arguments. We start both of the threads, we wait for them to finish, and we print how much time it took. Let's run this as well, because both of them will take time. Okay, so it took 75 seconds if run naively. Let's see if multi-threading can help in CPU bound task. Let's wait for it to finish. So let's make a note of it, right? It's approx 76 seconds for third. So this is 76 seconds. And let's see if multi-threading can help. So even multi-threading is taking around 76 seconds. So we'll just write 76 seconds. So our learning from everything till now is basically In IO-bound task, multithreading helps. In CPU-bound task, it doesn't help. And let's continue two more cases. So what we are just doing here is just checking if multiprocessing can help us in CPU-bound tasks. So it's similarly, we measure the start time, we measure the end time. In between, we are doing multiprocessing. We create two processes. The target is CPU bound. We give it the right arguments. We start both the process and we wait for both the process to finish. Let's run it and see. And while it is running, let's look at the next one as well. Let's see if multiprocessing works with IO-bound task. And same thing, the target is now IO-bound. The argument is correct for IO-bound. We create two processes, we start the two processes, we wait for the two processes to finish, we measure the end time, and we check how much time it takes. Oh, it runs in sequence, so we have to wait anyway, that's fine. Okay. So CPU bound task is taking 44 seconds. 44 seconds. So for CPU bound task, get some help from multiprocessing. And in IO bound task, it is taking 10 seconds. Okay, so we have all the numbers and let's conclude what we can. So the first thing is that multithreading helps in IO-bound tasks. It kind of works. In CPU-bound tasks, it doesn't help. Multithreading doesn't help, but the multiprocessing helps. Now, for IO-bound tasks, also multiprocessing works, but it's no better than multithreading in this case. So bottom line is multithreading is useful for IO-bound tasks. Multiprocessing is useful for CPU-bound tasks. So this is all about multiprocessing and multithreading in terms of the code we wanted to cover. I just wanted to add a bit about GIL in the notebook so that you can read about it. But just for completeness, I will read it here. I'll give the note to you later on. So let's go ahead. The global interpreter lock in Python serves a pivotal role by permitting only one thread at a time to access Python interpreter. This mechanism ensures secure memory management in multi-threaded environments, averting potential complexities arising from concurrent access to memory locations by multiple threads. Despite its merit in simplifying memory management, GILD introduces limitations, particularly in scenarios involving CPU-bound tasks in multi-threaded settings. The GIL's influence on performance is pronounced when executing CPU-bound programs, which are tasks like matrix multiplication and mathematical computation that heavily engage the CPU without relying on input-output operations. In such cases, GIL impedes the realization of true parallelism, limiting the potential performance gain that could be achieved in a multi-core CPU environment. However, the GIL proves to be less inhibitory in IO-bound scenarios where programs spend substantial time awaiting input-output operations. On the positive side, GIL offers several advantages. It simplifies memory management by allowing only one thread to execute Python code at a time. This reduction in complexity is particularly beneficial for developers who are spared the intricacies of synchronization mechanisms and the risk of data corruption associated with simultaneous access to shared memory locations. This is just saying that multi-threading implementation can be difficult. Furthermore, the GIL is optimized for single-threaded application, resulting in improved performance for programs that operate with just one thread. The reduction in overhead related to synchronization mechanisms and context switching enhances the efficiency of single-threaded Python applications. So GIL provides efficiency to single-threaded applications. Moreover, GIL facilitates compatibility with critical C extensions such as NumPy and Pandas, which are implemented in C or C++ and rely on the GIL for thread safety. This compatibility is essential for ensuring thread-safe memory management and preventing undesirable sequences of events in such libraries. So in essence, while the GIL introduces limitation in certain contexts, it offers tangible benefits such as simplified memory management, increased thread safety, and improved performance for single-threaded application, underscoring its significance in Python programming landscape. And with this long description of GIL, we kind of conclude on concurrency and multithreading. And now we'll move on to the next module. We're also finished with the Python module with this part. So let's start with probability in the next module.